Dear students, today's topic is quicksort, which is also known as partition, exchange, sort. Now, why it is called as a partition, exchange, sort? The reason being, the quicksort is using a mechanism where it is finding out its pivot element position, and once it is placing pivot element to its appropriate place, it is making two partitions, one on the left hand side of the pivot element and the other one on the right hand side of the pivot element. And after that, it is using again the quicksort to solve this partition or to sort these partitions. So that is why it is known as a partition, exchange, sort. We'll be taking one example where we'll be solving the problem of sorting with the help of given example. Let's say the example having the 8 elements. Now what we supposed to do is we supposed to arrange these elements in ascending order. So now as per the method, what we do is the last element from the list we consider as a pivot element, or we can say key element. Once we select this pivot element, then after we take two variables, one for iterating each element from lower bound of the partition to previous element of the upper bound, and the other variable we take which is pointing to the element which is previous element of the lower bound. So in this example, our lower bound is 1. So our I is 1 minus 1, that is 0. So in initial case, we have only single partition, the given data containing single partition. So in that, our arrays LB, lower bound is 1, and the upper bound in this example is 8. So our I is lower bound minus 1, that is 1 minus 1, 0. Now as per the mechanism, what we do is we compare the jth element with the pivot value or key value. So now if we say is A of j is less than equal to pivot, is less than equal to key element, is less than equal to key value, in this case no. So we just move further. So our now j pointing to next element, that is j equal to 2. Again we perform same kind of comparisons. We say is A of j less than equal to pivot or key value? Yes. So now what we do is we increment I by 1. So right now I is pointing to 0. So 0 plus 1 equal to 1. And then we exchange the value of ith position and jth position. So in this case 77 and 33 gets exchanged. So now we get is 33, 77, 44, 11, 88, 22, 66 and 55 is our pivot element, or we can say key element. Right now our I is pointing to position number 1, and now once we exchange this value, we continue this process. So now we have to increment j by 1. Again we compare jth position and pivot value. So is A of j less than equal to pivot value? Yes. So again we increment I by 1. So 1 plus 1, I is pointing to position number 2. And now we exchange the ith position value and jth position value. So in this case 77 and 44 gets exchanged. So we get 33, 44, 77, 11, 88, 22, 66, and we have 55 as a key value. Right now our I is pointing to position 2, and now we proceed further. So our j is pointing to position number 4. Now again, is A of j less than equal to pivot? Yes. Increment I by 1. So I equal to I plus 1, 2 plus 1, 3. And now the ith position value and jth position value gets exchanged. So 77 and 11 gets exchanged. So we have now 33, 44, 11, 77, 88, 22, 66 and 55. So our I is pointing to position number 3, and to proceed further our J is pointing to 5. J get increment by 1. Again we compare jth position and pivot value. Is A of j less than equal to pivot value? No, just increment j by 1. Is A of j less than equal to pivot? Yes. So now we increment I by 1, so 3 plus 1 4, and then ith position and jth position value gets exchanged. So in this case 77 and 22 get exchanged. So now we get 33, 44, 11. At the place of 77 we'll be getting 22, and at the place of 22 we'll be getting 77, 66 and 55. Now j gets incremented by 1. Is A of j less than equal to pivot? No. Then j gets incremented by 1. As we know that j will go up to the last position minus 1. So our last position in this case is 8. So j can go up to 8 minus 1, 7. So now here we have scanned entire list. So at the end of this scanning we get the final position of this pivot or key value. So that is the position which is I plus 1. So where this pivot gets placed? The position I plus 1. Here I is 4. So position 5 is the final position for this pivot value. So now we have to exchange the fifth position and the pivot value. So we get here 33, 44, 11, 22. Here we'll be getting 55, 77, 66, and at the place of 88 we'll be having 55, we will be having 88. So we got our pivot here. So now we are getting two unsorted array, one which is on left hand side of the pivot and the other one which is on the right hand side of the pivot. So in this case now we have this two partition, left partition having 4 elements and the right partition having 3 elements. Whenever we get a partitions, always the left partition will have a value which is less than pivot value, and the right partition will have a values which are greater than pivot value. Now once we get the different partitions, always we solve in the order from left to right. So now we'll be solving this left partition. So our last element we consider as pivot. I and j we have to set. J always points to lower bound. So in this case for this left partition the LB is 1 and UB is 4. So j points to LB, so 1, and I points to LB minus 1, that is 0. Now we compare jth position and pivot value. Is A of j less than equal to pivot? No. J gets incremented by 1. Is A of j less than equal to pivot? No. Again j gets incremented by 1. Is A of j less than equal to pivot? Yes. So what we supposed to do? We have to increment I by 1 and then we exchange jth position and pivot position. Jth position and ith position. So 33 and 11 get exchanged. So we'll be getting 11, 44, 33, 22. Now j gets incremented by 1, but as we know j can go up to the UB minus 1. So our UB is 4, so j can go up to 3. Now entire partition has been scanned. So at the end of the scanning we get the final position of this pivot value, and that position is I plus 1 position. Our I is pointing to 1, so 1 plus 1, 2. The position number 2 is the final position for this pivot value. So now we'll be having 11, this 44 and 22 get exchanged, so 22, 33 and 44. Now pivot is at its final position. So now we are getting two partition. One partition on left hand side of the pivot and the other partition on the right hand side of the pivot. Now we have a left partition of 22. As we know, if list having single element, it is always sorted. So we'll be opening this partition. So we are writing 11 as it is, 22 as it is, and then we'll be having 33 and 44 as a part of right partition of 22. The remaining value remains as it is. Now from left to right we have this partition in that the last element is considered as pivot element. Now for this partition, LB is 3 and UB is 4. 1, 2, 3, LB is 3 and UB is 4. So J is equal to LB, which is 3, position number 3, and I is LB minus 1, 3 minus 1, 2. Now we compare jth position and pivot value. Is A of j less than equal to pivot? Yes. Increment I by 1. Exchange ith position and jth position. In this case, 33 exchange with itself. And then j gets incremented by 1. But as we know, j can go up to this upper bound minus 1. So here the scanning of this list gets over. So we got this final position of 44. That is our pivot value, and that position is ith plus 1. Now our I is pointing to 3. So I plus 1, 3 plus 1, 4. That is the final position for this pivot value. So now we have one partition on left hand side of this pivot, and on the right hand side of pivot is an empty partition, because on the right hand side of the 44 there is no other element in this partition. So now we have this left hand side of partition of 44 having single element, and as we know, the single element partition is always sorted. So now we have only one partition to solve. In this partition, again we'll take last element as pivot element, and LB is 1, 2, 3, 4, 5 and 6. So our J is 6 and I is LB minus 1, that is 5. We check, is A of j less than equal to pivot? Yes. What we do? We increment I by 1, so I is pointing to 6, and then we exchange ith position and jth position. So in this case, the 77 gets exchanged with itself. Now j gets incremented by 1. Again we compare jth position and pivot value. Is A of j less than equal to 88? Yes. So again what we do? We increment I by 1, so I becomes 7, and ith position and jth position gets exchanged. So in this case, 66 exchange with itself. Now j is pointing to the previous position of pivot. So entire list in this partition has been scanned. So now we got final position for this pivot value 88, and that is ith plus 1 position. 7 plus 1, 8, and 88 is also placed at position 8. So pivot position exchange with itself. So pivot remains here only. So now we have elements in this order where we have left hand side partition of this 88 where we have 77 and 66. As there are no other elements on right hand side of 88 in current partition, the right partition of 88 is empty. Now we have one partition to solve, in that 66 becomes pivot, and the LB for this partition is 6. So J becomes 6 and I becomes 6 minus 1, 5. We compare jth position and pivot value. Is A of j less than equal to pivot? No. So now j cannot move further because all the elements except pivot has been scanned in this partition. So at the last we got final position for 66, and that position is ith plus 1 position. I is pointing to position 5, so 5 plus 1, 6. So now the 6th position is the final position for this pivot value 66. So the 77 and 66 gets exchanged. So now we have 66 here, 77 here, 88. Now on the right hand side of 66 we have one element in the partition, that is 77. On the left hand side of this 66 there are no elements, as before jth position there are no other elements in current partition. Again we have one partition but with single element, so that partition will be opening. So final sorted list we got, that is 11, 22, 33, 44, 55, 66, 77 and 88. So this is how we can sort our data in ascending order with the help of quicksort, or we can say partition, exchange, sort. Now we'll be moving to algorithm. So in order to write quicksort algorithm, first we need to write a partition algorithm, because each time we are putting our pivot to its appropriate place and we are making two partitions. So let's say we have array A with LBP and UBR. So P denotes lower bound and R denotes upper bound. So what we do very first, we decide a key element, or we can say pivot element. What is key or pivot? We say the last position value. So we say A of R. Then we set J and I. So what is value of I? I is LB minus 1. What is our LB? P. So P minus 1. Then our J starts from LB and then it goes up to UB minus 1. And every time we do comparisons. So we have to iterate some steps for J equal to lower bound to upper bound minus 1. So we write iteration here for J equal to P to R minus 1. And we know that every time J gets incremented by 1. So step 1. What we do, we always compare A of J with pivot or key value. So we say we compare this A of J and key. If A of J is less than equal to key, then what we do, we increment I by 1. Correct? We increment this I by 1. Then after we exchange ith position and jth position. So we say exchange A of I and A of J. If this condition is not satisfied, we just simply increment J by 1. So what happens in this case, if let's say J equal to P, then it will check that is A of J less than equal to key. If that condition is satisfied, then I is incremented by 1 and then it exchange ith position and jth position value. If this condition is not satisfied, then simply it increments J by 1. So whether condition is satisfied or not, every time J gets incremented by 1. When this entire iteration gets over, meaning to say when J starts from LB and it goes up to UB minus 1, all the comparisons are done. At the last, the final position of pivot we got, and that position is I plus 1 position. So now we have to exchange I plus 1 position and the pivot position value. So we say exchange A of I plus 1 and pivot value. So we may say key, or we may say the rth position value. So once it is done, now we'll be informing that where the pivot is placed. We know where the pivot is placed, ith plus 1 position. So we return I plus 1. This is what partition algorithm. Now Quicksort is using this partition algorithm. So let's write Quicksort algorithm. Now for Quicksort, what we say, we have array with LB and UB, or we may say P and R. Correct? I may say P or and R, the lower bound and upper bound. For Quicksort, what we do? First we do partition. Correct? First we do partition. So for partitioning, we'll be using partition algorithm. So we say partition. As we know, the partition algorithm requires 3 arguments: the array itself, lower bound of current partition, and upper bound of current partition. Very first time we'll be having entire list. Its lower bound is P, upper bound is R, which will be returning the position of pivot. Let's say we store in F. Now once partition is done, after partition the pivot comes to the position F. So now we have 2 partition, one on the left hand side of the pivot value, other one on the right hand side of the pivot value. So now we'll be calling Quicksort 2 times. One for left hand side of partition, that is A comma. Now if we have a list starting from lower bound P up to upper bound R, in between, let's say these are my elements. This is position P, this position R. After exchange, I say I have this P, this position R, and I got pivot here at position F. So I have 2 unsorted partition, one on left hand side of F, one on right hand side of F. So the left hand side partition starts from P. So lower bound for that partition is P, and the upper bound is just before F, that is F minus 1. So what about the right hand side of partition? So it starts from F plus 1. So LB for that partition becomes F plus 1, and the upper bound remain same, that is R. So again we call a Quicksort where we say we have to solve for right hand side of partition. Sorry, the right partition of this pivot. So that is starting from F plus 1, that is lower bound is F plus 1 and upper bound is same, that is R. Now we solve this if and only if we have something to solve. What do you mean by something to solve? If we have a list with more than one elements, P always is less than R. P always less than R. Let's say if there is a partition with single element. So P and R both are pointing to same element. That means P equal to R. So what I said, let's say we have more than one elements in our partition. So in that case, P is less than R. So this condition satisfies. If we have a single element in partition, so P and R both are pointing to same element. As we know that when we have a single element, it is already sorted. So for P equal to R, there is no need to solve this partition. No need to sort this partition. So there are three possibilities when we compare P and R. P less than R, P equal R, and the third possibility is P greater than R. Now when P greater than R condition gets satisfied, it happens in the case where we say we make a partition, correct, which is non-existing partition. When partition becomes empty partition, correct. So in that case, P greater than R gets satisfied. Such kind of empty partition we never solve. Similar way, the single element partition we never solve. So what we need to solve is only P less than R. So what we can write in this quicksort algorithm, if P is less than R, then and then we solve this quicksort so this is how we solve the sorting problem with the help of quicksort or partition exchange sort. So if you have any doubt, you may revert me. I'll be giving you one example to solve, or I can say the exercise to solve. Let's say the list of elements are so there are 6 elements. You need to sort these elements with the help of quicksort. Put these elements in ascending order, correct? So I can say sort in ascending order using quicksort. Now same way I'll be giving you another exercise. I'll say sort following data in descending order using quicksort. Let's say values are so we have 7 values to sort. Now what will happen when you solve this, you sort this data in a descending order? What kind of changes you need to do in your algorithm? What we need to do is we need to change the condition over here. When we sort our data in descending order, we say if a of j is less than equal to key, and then we exchange ith, we increment I by 1, and then we exchange ith position and jth position. When we sort our data in descending order, what we need to do is we need to change this condition. Instead of less than equal, we'll be saying if a of j is greater than equal to key, then perform this exchange once you increment I by 1. So this is what a quicksort. If you have any doubt, you may contact me.